to this session. Today, we will learn about quick sort, and we have already seen merge sort. In merge sort, the heart of the merge sort was merge procedure. Just like that, in quick sort, we'll have another procedure called partition procedure. That is heart of our quick sort algorithm. Okay, so. Um, why it is named quicksort? Quicksort is called quicksort because it is better than many algorithms in small input. In case of small input like 100 inputs or 10 input, it is better than merge sort. And there are many. There is one more reason to call it a quicksort that I will explain it in the end when we have already discussed these algorithms. So let's see what is an algorithm here. So I'm going to write an algorithm here. What is the algorithm or the heart of the merge or the quick sort is partition algorithm. So let me write that and I'll explain you with the example. So there is this algorithm partition and these are the arguments. This one is your array that we have passed, and this one is the starting point of the array. This one is the ending point of the array. Now, we'll see the algorithm. We'll assign a pivot element. A pivot element that is our last element. Last element to x. Okay. Then I is a variable that will start from starting point minus 1. Why we are doing this, I'll explain it with the help of example. Okay, so and there will be loop starting from the starting point to the ending point minus 1, and in this loop we will compare each element. This is j equals to 3, so j will get incremented one by one while this loop will run. Okay, so if we write this, a of j is less than equals to x, then we have to increment I by 1. Then we have to increment I by 1, that is I equals to I plus 1, and then we can exchange some values that are a of I with, that is nothing but swapping. Because this is an algorithm, we are not writing it in any programming language. So I am simply writing here exchange a of I with a of j. What does this mean? This means the element at ith position and element at jth position in an array A will get swapped. Will get swapped. And after that we need to exchange again, exchange a of I plus 1 with the last element, that is a of r. A is our array. Okay, and then we will return this position. Return I plus 1. So this is where our for loop ends. This is where our for loop ends, and this is where our algorithm ends. Okay, this is our algorithm. So how this will work, let me show you that with the help of example. Let me show you that. Okay, so let's see that. So here, consider this example where we have an array and how to perform a quick sort. What is a quick sort actually? What is a quick sort actually? So in this we can learn, we'll take the element from the last position. Let's say this is our element, or given an array, in an array, if we want to apply quick sort, what is sorting again? To arrange the elements in ascending or descending order. And if we want to sort these elements and an array is given and we want to apply quick sort on it, so quick sort will take the element or any element. Let's assume it is the last element. if quicksort is taking the last element, it will take the last element and put this element in its own position. Put this element in its own position like this. If this element have the position in the center, it will put this element in the center in such a way that all the elements to the left of this element, this this element that we have placed in its correct position, all the elements in the left are less than this element, and all the elements that are in the right side of this element that we have placed in its correct position are greater than this element. So all the lesser elements are on this side and all the greater elements or more elements, the value that having more value than this element are at the right side. Then on the left side again we will apply the quicksort, and on the right side again we will apply the quicksort. So this is the quicksort. We'll see it with the help of example. So what is this again? We'll take a last element and put it in the its own position. After sorting, we will put this element in its own position. Then all the elements, these are not sorted, but these are less than this element and these are less than more than this element. But in the case of binary search, all the elements are sorted already. But here the elements may not be sorted in this right sub array, and elements may not be sorted in this left sub array and right sub array. But these elements are less than this, and these elements are less than this pivot element. Okay, we'll see the example. Let's see the example. Let's see. Let's say these are our elements 9, 6, then we have 5, 0, 8, 2, 4, and 7. These are our elements. We need to sort these elements using quicksort. We need to sort these elements using quicksort. Now, what does our algorithm say? Algorithm says assign a large. This is the starting point. This one is starting point. These are the index. These are the index. Now this one is our starting point P, and this one is our ending point R. Okay. Now what do we want to do here? So our next step in this algorithm is take x equals to a of r. What is r here? A of r is 8. A of r is 8 and a of r is 7. So in x we'll assign a of r, that is r is 8 and value of a of 8 is 7. So our pivot, what is pivot? Around pivot the whole list will revolve. That is just like the axis of earth. Around the axis of earth, the earth revolves. So like this is the center point, and all the elements to the left and all the elements to the right revolves around this pivot element. Okay, this one is a pivot element. So that is another method to do the sort. So you will be able to see this one is a easier method. You have already seen some methods where you to take an element and compare it from the left side and then from the right side. That is a complex method according to me. This one is a very easy method, but you can use any method. Okay, so this is according to your book, that is Introduction to Algorithms by Coleman. Okay, so this is according to that. Now we have taken this first step, that is x equals to a of r. X equals to a of r, and in this next step is I equals to p minus 1. What is I and what is p here? P is equals to 1. So I will be p minus 1, that is 1 minus 1, that will be 0. Okay, value of I will be 0. And in next step, there is a for loop that starts from j equals to p. Now J's position is this p, j equals to p. and I position is this 0. J is this and I is 0. And element at A of J. Now J is 1 because J is equals to P. So J is 1. So element at this first position is less than or equals to pivot element. What is our pivot element? That is 7. What is our pivot element? That is 7. So we are comparing 9 with 7. So is it less than 7? No, it is not less than 7. Okay, we are comparing 9 with 7. That is not less than. So what we will do, we will be doing, we will be comparing this pivot element with all the elements. And if we found a smaller element than pivot element, smaller element than pivot element, then we will do some action. Okay, so in this case, we will be doing nothing because our condition is if this is less than or equal. This is not less than equal. So this is false. So what will happen then? This for loop will end and it will run again for j plus 1. Okay. Then j will become the next element. This is j now. So j is 2 now. Okay. J is 2 now. And a of j will be 6 now. 6 is less than 7. Then what should we do? I equals to I plus 1. I equals to I plus 1. So I'll change I. I is currently 0. It will become 1 now. And then exchange A of I with A of J. What is A of J here? That is this one. So we will replace, exchange these two. So 6 will come here and 9 will come here. What we are trying to achieve here is whatever element we found is smaller than this pivot element, we'll take it out and put it in the left side of the array, because we need all the elements to the left of pivot should be less than this pivot element. Okay. In next iteration, let's see that again. I'm going to rub it. Now we know our pivot element is 7 and our j will be the next point and I is here. This is our j. Okay. So at a of j we have 5 and we'll compare it with the 7. Is it less than 7? Yes, it is less than 7. So what we are going to do here is we'll increment I by 1 and replace this element with the pivot element. Okay, oh sorry, the element. So we'll exchange these two. 5 will come here and 9 will come here. And after exchanging, j will get incremented again. What will be j now? So j will be here now, 0. And is 0 less than 7? Yes, 0 is less than 7. What we are going to do here is we'll increment I by 1 and we'll replace these two, interchange these two. So 0 will come here and 9 will come here. In next step, how long we have to keep on doing this till r minus 1? What is our r? R is ending point. And till we have reached here, we need to repeat these steps again and again. That's why we are using for loop. Okay. So for 8 now, 8 is not less than 7. So we are not going to do anything here. Then they will get incremented. Here we'll have 2. 2 is less than 7. What we need to do is we need to increment I by 1. So we will increment I by 1 and replace these two. What are these two again? We need to interchange these one. 2 will come here and 9 will come here. How long we have to keep on doing this till the last element is 15. So this is our last element because we have run loop from the starting point to r minus 1. Starting is p, ending is r minus 1 will be this element. So for this is our last iteration for this loop. This is smaller than pivot element. So what we are going to do, we are going to increment I by 1. We are going to increment I by 1 and replace this with the jth element, that is this 4. So 4 will come here and 8 will come here. Okay. Now the elements are not sorted yet. But what will happen? What is the next step? Once we are done with our loop, loop is finished now. What is next step? Exchange a of I with a of r, a of I plus 1. That is this position. We can see at this point, all the elements, including this one, all the elements to the left of this element are smaller than 7, are not sorted, but these all are smaller than 7, and all the elements on the right side of this position are greater than 7. So what will be the correct position of 7? That will be I plus 1. So that's why we have written exchange I plus 1 with A of R, that is our last element, or that is our pivot element. So what we will do, we'll replace this one. We can see all the elements to the left are smaller than, and all the elements to the right are greater than this pivot element. Okay, or we have two subarrays, left subarray and right subarray, and all the elements in the left are smaller than this pivot element. All the elements to the right are greater than the pivot element. But the 7 is at its own position. Uh, Once we are done with sorting, once the elements are sorted, this is the correct position of 7. So we have placed one element in one pass at its right position. So that is our partition procedure. And now we'll call this partition procedure again on the left subarray and right subarray. We keep on doing this until our elements are sorted. So this is the partition procedure. This is the partition procedure. We need to find out the correct position of pivot element so that we can divide the list into two parts where the elements to the left are less than the pivot element and elements to the right are greater than the pivot element. So this is called partition procedure. This is also example of divide and conquer approach, just like merge sort. What are the differences that we'll discuss just now after this. Now we have understood this algorithm partition algorithm. This can be used in quicksort. This is not quicksort. This is only partition algorithm, the heart of quicksort algorithm. And just like the merge procedure we have discussed. Now we will discuss the quicksort algorithm. What is a quicksort algorithm? Okay. So the complexity of this will be order of n. Order of n because there is only one loop in it. Okay. And now we'll see the quicksort algorithm. This is our quicksort algorithm. We'll write quick sort and we'll pass the array and the starting point and the ending point. And we'll write if p is less than r, this starting point, because we are decreasing the list gradually. So this eventually will become less than r. Then only we will stop, because this is a recursion based algorithm. We are using recursion here to make it work faster, to make it work better. We are using recursion. So this is the exit condition of that recursion. The recursion will only stop when this condition is not met. Okay. Otherwise, it will keep on doing. It will keep on calling itself again. What is recursion? Function calling function itself again. So this is partition, and we'll write A of P of R. So we are applying partition procedure, and it will return some value of Q, the middle point where the element is at its own position. That one element we have done using this partition algorithm. Okay. Then we will call quick sort. Quick sort for the starting point will be same, but we'll call it for the left subarray, the elements at the left side of this Q position. And we will do quick sort for, we'll call quick sort for one more, that is from Q plus 1 to R. Okay. And we are done with it. This is our quick sort algorithm. I'll tell you one more thing. I'll show you what is being done here. What is being done here? Let's see right. What is being done. What is being done? Here? What is being done 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 here? So let's say this is our list and we want to sort this list. And this is our element, pivot element, that is R. So we are by using this procedure, we are getting this element to its right position. We are getting this element to its right position. This is its in the right position. R's right position. Let's say this is Q. Now this one was P, starting point was P, and ending point was R. Now after applying partition procedure, we came to find out that this one is Q now. Q is the right position of R actually. Now I will divide this into further parts. That will be from Q to P to Q minus 1, that is left subarray, and the right subarray will be from Q plus 1 to R, the right subarray. Okay, then we'll apply using these P to Q minus 1, we'll apply quick sort again for this, and quick sort will call partition again. Okay, and we'll apply quick sort for this as well. This is the right subarray. Okay, for left subarray and for right subarray, we have used the partition to divide that, and for left subarray, we again call the quick sort function again, and but now new P and new R will be there. That will be P will be passed there. That will be starting point, and Q minus 1 will be the ending point. Again, further, this will keep on doing this. We divide this list again and find the right position of pivot, and there will be two subarrays, and from Q P to Q minus 1 and Q plus 1 to R. Similar thing will be done on the right side of the right subarray of after Q. So we will keep on doing this until this condition is met. That is our exit condition of the recursion. Okay. So quick sort will be called for right subarray. Quick sort will be called for left subarray and right subarray both. Now, what is the difference between merge sort and quick sort then? In merge sort, the list is always divided into equal parts. Two equal parts. List was divided into always two equal parts. Okay. But in the case of quick sort, that is not for sure. List will not get divided into equal parts. It could be greater in one side number of elements, could be greater in left subarray and could be greater in right subarray. So we were passing the middle point first in the merge sort. But here we need to calculate the merge procedure was at the last after dividing the list. But here the list will divide it on the basis of on the input of this partition algorithm. This partition algorithm will tell us from where to divide the list. Okay, so that is the difference. In merge sort, list will always be divided into equal halves, but in quick sort, size of sublist will vary. It will change from example to example. Let's see one more example then. Let's see one more example then. So what is the other example? Let's see that. Let's say these are the elements 5, 7, 6, 1, 3, 2, and 4. And this is the index. Okay, this is the index, and these are the elements. Now we'll use this quick sort algorithm. Okay, we'll use this quick sort algorithm. What is this algorithm? Let me write it here. So first of all, quick sort will be called. Quick sort will be called for P is 1, P equals to 1, and R equals to 7. I'll write 1 and 7. Quick sort will be called. Okay, P equals to R, and P equals to 1 and R equals to 7. Now what will happen? We will call, the function will call first partition procedure. Partition procedure, that is this one, and it will return a value 2. What will be the value of 2 in this case? Let's see that. After seeing that, then only we can tell what will be the these two recursive calls. What will be these two recursive calls based on the value of q? Because we have written q equals to partition, and partition, if you can go back to the algorithm of partition, there we have written return I plus 1. So I plus 1 will be returned here. So that will be the value of q. So we need to find out the value of q first. We can see with the help of this example, and this is our pivot element, let's say x, and this is our I, and this is our j. That was partition algorithm. Okay. So we compare this with this. That is greater than 4, so it will not do anything. 7 is also greater than 4, it will not do anything. 6 is also greater than 4. This will also not do anything. 1 is less than 4. So what will be done here? I will be incremented by 1, and these two will get interchanged. 1 will come here and 5 will come here. Okay. Then what is the next step? Now we can see what is the next step. So j will get incremented, and 3 is less than 4. What will happen? I will get incremented, and these two will get interchanged. 3 will come here and 7 will come here. Okay. Now j will get incremented because this is r minus 1. We have seen till r minus 1 only will loop will run only till r minus 1. So this is also smaller than the pivot element. So I will get incremented, and these two will be replaced. 2 will come here and 6 will come here. Now we can see after I plus 1, this is the correct position of 4. So I plus 1 and this element, last element will get swapped. This is after 4 loop. So 4 will come here and 5 will come here. Okay. And this will be our I plus 1, and this value will be returned. 4 will be returned here. Okay. 4 will be returned here. So if 4 is returned here, 4 will be returned here, then quick sort. This is q. Now we can see quick sort will be called for p to q minus 1. So what is q minus 1 in this case? What is q? Q is 4. So quick sort will be called again for 1 to 4. And we have checked that 1 is less than 4. That is true. That's why we are doing recursion again. Otherwise, if this condition is not true, we will not do any further recursion. Okay. So if this is this, and what will be the second, the right sub array, that will be q plus 1 to r. What is q? 4. So that will be quicksort will be called again for new values, that is q plus 1, that is 5, and r is 7. Okay. So this is how it will be done. So this is the first recursion only. So we have seen till now that these recursion calls will be made, but after this quicksort will run again. Quicksort will call quicksort again, but for different set of values. That is starting point is 1 and ending point is r. So here will pass 1 and 4. So for 1 and 4 again partition will be called. Partition will be called again for 1 and 4. So for from this 1 to, sorry, this is 4. So there we can write q minus 1. That is 4 minus 1 is 3. So that will be from 1 to 3. So list will be from 1 to 3. Now how we will find out the right position of pivot? What is pivot element? That is the last element in this. The list from 1 to 3. List from 1 to 3. 1, 2, and 3. There are 3 elements in this. How can we apply quicksort on it? We'll have to apply partition on it. What is partition? We take the the last element as a pivot element, and this one will become our j, and this one is our I. I is less than p minus 1, that is 0. Okay. So what will happen? We'll check if this element is less than this. That is true. So what we'll do? We'll increment I. I and j are now same, and we need to replace a of I and a of j. So one will remain at its own position and j will get incremented. This will become j because 3 is greater than 2 and nothing will be done and list is finished because these are the three elements. Only three elements are there in this list. So what will be returned? Right position of pivot will be after this I, that will be I plus 1. So here we write 2 and here we can write 3. And now we are done. So I plus 1 is 2, 2 will be returned here. So Q will be 2 here. So Q is 2 here. Now we can divide the list further. So what? How can we divide the list further? We will call quick sort again for 1 to Q minus 1, that is 1, because Q minus 1 will be 1, and start from P only, that is 1. P is 1, R is 3, and this is also less than R. We have checked this condition. This is less than R. Okay, and then from P, that is 1, to Q minus 1, that is also 1, because Q minus 1, 2 minus 1 will be 1. So quick sort is called again. Okay, then there is one more quick sort in this, because Q plus 1 to R, that will be from Q is 2, 2 plus 1 will be 3 to 3. Now again this function will call from a different set of values for 1 and 1. 1 and 1 is not less than R, because these two are equal. This will not call any function again further. So recursion will stop here. Recursion will stop here also, because this function will not also call, because the exit condition is not met. This is the exit condition is true now, because 3 is less than 3. That is not true. So it will get exited from this recursion. Now what will happen, because we are done with this portion, this function was left, so this function will run again. What will happen in this case? So there will be three function calls again. First there will be a partition from 5 to 7. From 5 to 7. So 5 is this and 7 is this. We have replaced the size. This was 5 is this. It is okay. Now from this to this is our P now. 5 is our P and 7 is our R. Okay. 5 and 7. So from this, starting from 5 to 7, so our new starting and ending point are 5 and 7. So we can see 5 is less than 7. So this will work. So we'll calculate new partition. How can we calculate new partition? Because this is J and 4 will be I. I will be equals to 4, J is equals to 5. Okay. Then we'll compare this with the pivot element, that is our last element, that is greater. We have to do nothing in this case. Okay. Then J will get increment by 1, incremented by 1. Then we'll compare this element with this element. This is also greater than 5. So we'll do nothing in this case. And here we can stop, and I is 4, still 4. So we'll at last we will increment I by 1 and replace these two. This is 5 and this is 7. And this one is the right position, that is 5. So 5 is the right position. And further we will call quick sort. We will call quick sort for 5 to 5 plus 1, that is 5 to 5 minus 1, sorry, that is 4, and 5 plus 1 to 5 plus 1 to R, that is 6 to 7. 6 to 7, that is 6 to 7. That is 6 to 7. Let me write that. This partition is from 5 to 7, and Q's value is 5 here. And quick sort for from P to Q minus 1, that is 4. Q minus 1 is 4. And from Q plus 1, that is 6 to 7. Okay. And we can see for this, the next function is 5 to 4. So 5 is less than 4. That is not true. So this is the doesn't have any meaning. There is no list such list. 5 to 4, that will be a backward list, but we need a forward list. Okay. That is 6 to 7. 6 to 7 is true. So we need to do the same thing for 6 to 7. That is partition procedure will be called. If we call partition procedure, what will be the answer of Q in this case? This is our J and this one will become I, and it will be compared with this element that is a smaller element. So what we'll do, we'll increment I and replace this one with the this one. Okay, and this 6 will remain at its own position. There will be no change. Then we will return I plus 1, that is 7, and replace this one. So I plus 1 and pivot element are same, so this will remain at its own position and 7 will be returned. So 7 will be the value of Q, and quicksort will be called again. Quicksort will be called again for 6 to 6 and for 7 for 7 plus 1, that is 8 to 7. So there is no such list because condition will not be met here. So our core recursion will stop here, and we can see our elements are sorted now. Our elements are sorted now. We can see our elements are sorted now. These elements are sorted because we have seen I j equals to this, and our elements are sorted. So what will be its analysis? Let me write that again for you. I'm going to erase this one. Let me write this. This is for the tree with sort. Now we are going to do the analysis. This kind of analysis, that is, what will be the space complexity and what will be the price of this. So, if this is the case, and we have just fold this one. So this is a recursion tree. This is called recursion tree. How the recursion will work. This is our recursion tree. Now we can see space-time complexity and what will be the space complexity. So this list is not divided into equal halves. So in best, there will be best case, but in merge sort, there is no best case of this space and space complexity. But in this, there will be best case of space complexity. How much memory will it take? It is not taking any other time, other algorithm than this other space than this are the input array. This is also in place algorithm. So we are replacing the elements on the same element. We are not taking any additional or auxiliary array. Okay. So in that case, the complexity will be order of 1. But but we have seen in the merge sort, the complexity was order of n plus order of log n, and log n because in space complexity we need to consider the smaller value, that is this one. So smaller space will be taken. So this was our complexity. But in this case, there is no general memory taken here, but there will be many function calls. There will be many function calls here. Many function calls. This is space complexity. Space complexity. Many function calls will be there, and it is, let's say, best case will be that list will divide it into two equal halves. If there are n elements, there will be n by 2, two lists of n by 2 elements, two lists of n by 2 elements. And because these recursion calls get stored in a stack one by one, so just like merge sort, this will also store all the recursion calls in a stack. But if the best case is this, the list always get divided into two equal halves, then the the complexity will be log n, order of log n, big O of log n. Okay, big O of log n. That will be the complexity. Why? Because the height of tree is log n. That I've already told you in the previous video. Height of tree is log n. That many recursion calls, that means spaces are required in the memory to the height of tree. Or we can see number of levels in tree. Number of levels in tree is equals to stack entries required. How many stack entries are required? That we have already discussed. So complexity will be order of n. If the tree is balanced, if the tree is balanced, if it is not, then what will happen? Let's see that. That will be the worst case actually of space complexity. Worst case of space complexity. What will happen in that? So in that case, the tree is not balanced. So what will happen in that? So if there are n elements, what will happen? One element is there, and there is this n minus 2 elements, because one element will get sorted. Okay, and one element is at this side, and there will be 1 minus 4, and so on up to there will be n elements. So n spaces will be required. N spaces will be required. So this is the worst case. The complexity of worst case is order of n in case of space complexity. Okay. Now let's see the time complexity. Let's see the time complexity. So we need to write that algorithm again, quicksort algorithm. So I write it in the short form. If p is less than r, then we have to call partition for p and r, p and r, and then we call quicksort again for p to q minus 1 and from q plus 1 to r. Okay. This was our. So we'll take the worst case first. What is the worst case? Let's see that. What is the worst case? We'll take best case first. Okay. What is best case? So this will take some constant time, and this will take order of n time, the go of n time. That I've told you what is the complexity of partition as well. Then this will take. I guess the list is what is best case. This is the best case in terms of if list is getting divided into two equal halves, that is the best case of quick sort. Why this is best case? I'll tell you that. Okay, but it is the best case. So if this is taking Tn time, this half list will take n by 2 time. N by 2 time. So this is same equation as we have in the merge sort, and we know the recursion tree gives us the output order of n log n. So this term will come out like this: order of n plus 2 n by 2. Again, by master theorem or by recursion recurrence relation or recursion tree method, we can say this was theta of n log n. theta of n log n. That was our answer. That is the best case now. Best case. In merge sort, best and worst case was same. That's why we have used theta there. Theta is representing the average case. So I've already told you in the first lecture that whenever we have same best and worst case, we'll write theta of n log n. But in this case, in best case, the same equation is there as that was in the merge sort. So the best case of quick sort is equals to the average case of merge sort or the worst case of merge sort. That's why it is called quick sort. This the best is equals to the worst. Its best is equals to the worst. Okay, so that's why it is called the best. The quick sort is called quicker than merge sort. Now we will see the worst case. There will be many examples of worst case. In worst case, the list will divided into not divided into two equal halves. So let's say this is list and we have zero elements at the left sub array and there is n minus one elements in the right sub array because one element will get sorted. Only one element will get sorted and there is no element of the left sub array. And similar thing that is called skewed matrix in your data structure. So 0 and n minus 2. If we will keep on doing this, this is not the most of the cases. This is actually the worst case, but there will be very few cases in which list is not divided. The list is divided in this case. That's why quicksort is better because the average number of examples will be solved with the best case. Average number of examples will be solved with the best case, but worst case will be very few examples. So what are those few examples? I'll tell you. So after this, there will be at last only one element. So before one, there will be two elements. Before two, there will be three elements. Because this is decreasing by one. At last, there will be one element only. Before that, there will be two. Before that, there will be three. If I add all these, this is nothing but sum of n natural numbers. That comes out to be n into n plus 1 divided by 2. That is worst case, order of big of n square. So in worst case, it is taking more time than the merge sort, but the most of the cases will not be worst cases. Let me give you one example. What will be the example of the elements in the case of worst case in quick sort? Let's say if elements are sorted in reverse order. So what will happen then? What will happen then? This is the pivot element. So it will be compared with this one. So this is J and this is I. Because this is greater, nothing will be done, and J will be incremented. This is greater, nothing will be done. 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 Okay, nothing will be done. And at last, I will be incremented, and these two will be replaced. So this will be 1 and this will be 6. So if there are n elements, in left sub array there will be no element. In left sub array there will be no element, but there will be n minus 1 elements in the right sub array. And we'll keep on doing this. If we keep on doing this, this will come out to be order of n square. Order of n square. So the worst case of quicksort is order of n square. And this was the example of worst case. And what if the elements are sorted in this order? Already in ascending order. Then also it is the worst case. Then also this one is the worst case. Let's see that this is the pivot element. We'll compare it with this. This is smaller, so and this is I and J. So I and J will be I will be incremented and these two will be swapped. This will stay here. Okay. Then J will become this, I will become this. Again, we have to replace it and increment it, and these will get at same position. 2 will be at same, and so on. So this is the correct position of 6. Now, what will happen after interchange? This will become our pivot element, and so on. So if there are n elements, there is 0 on the right and n minus 1 on the left side, and we'll keep on doing this in this example. And this one is also an example of worst case. If all the elements are equal, then also it's example of this same example. Worst case. So these all are the worst cases. Okay. Now let's see the PPT. This is our PPT related to quicksort again. We have already seen it uses divide and conquer strategy. It divides the problem into smaller problems, and then after dividing it solves the problem and then again combine the solution. And we have the sorted list. This is the algorithm that we have already seen. And there is a subroutine called partition. And in partition, this is the example of partition algorithm. And in analysis, we have seen that if the list is divided not into equal halves, then that will be the worst case. And even if there is one element on the left side, that is also the average case. So that's why quicksort is better than all other algorithm, and that's why it is called quicksort. We can see this equation will come, and this is n square. This is the worst case because there is no element on the left side. If there is one element and 990 element on the other side, 999 elements, let's say 1000 element on the other side, and then also it is the average case. We can prove that. Okay. Then best case we have seen that it is nothing but this tree, that same tree that we did in merge sort. So it is theta of n log n, theta of n log n. This is base 2, okay, because there are 2 children of every node. So that is quick sort. There is one more quick sort algorithm, that is let me share that one. That is called randomized quicksort. That is called randomized quicksort. Now, instead of taking the last element, we'll allow the compiler to choose random element. That is called randomized quicksort. So, I'll see here, you can see a random element out of the list of array is picked, and that element is replaced with the last element, and then again quicksort is performed. What is the fun of doing this? The fun is that it will always come closer to the best case. There will be no such case of worst case in this by using this method. There will only be the best case, that is theta of n log n. So n square will not be the in the most of the cases. So this is the master theorem that we are yet to discuss. We'll discuss in the coming lecture. Okay. So that will be all for today, and thank you.